So our learning goal today is I can graph and transform quadratic functions. So we're going to be actually using the graphing calculators to help us make the graphing and the note-taking so we can save some time. But the types of transformations we have to talk about with our quadratic functions are, I want you to put a box around this at the top. This is the important information. Compared to the function f of x equals x squared. What's that function called? F of x equals x squared.
Means y equals.
Means y equals x squared. It's a member of a family. Which family member is it? We might have to go back to our 8.1 notes. We'll find them. 8.1 notes. What's this? What is this f of x equals x squared? Gotta roll. And it's important that we understand what its role is.
F of x is the function of x.
No. Remember what the function f of x equals x squared is. Maybe I'm wrong. It was 8.1 notes. Maybe you don't find 8.2. Would you tell us what f of x equals x squared is? It's the parent function. Where are those notes at, Julia? 8.1, the very first set of notes we took in this chapter. Find them, not the 8.1 notes, continue with the 8.1 notes, right, Julia? Okay, find those notes. It says f of x equals x squared is the parent function of the quadratic family. So it's the one that is the most basic quadratic function, and from that, it goes through transformations to get other quadratic functions, okay? So, compared to the function f of x equals x squared, the parent, a quadratic function will become narrower or wider, skinnier, I think that's an easier word to say than narrower, skinnier or wider, based on what does it say there in your notes? What controls the skinniness or the width, the fatness, the width of a parabola? What controls it? What does it say there in your notes? Right here in today's notes, part we just put a box around. What controls that? The value of a. And we're actually going to also say the absolute value of a, because remember the negative sign or the positive sign, what part does that control? Whether it opens up or it opens down. So if it's a positive a, we know it opens up. If it's a negative a, we know it opens down. Now when we take the absolute value of each of those a's, we say which one of those, what are their absolute values? Well, absolute value means what again? Distance from zero. So which one's further away or which one's closer to zero? That's what we're going to use the absolute value of a to decide which one's wider than the other or is it skinnier than the other. Okay, and then it will translate up or down. What does translation mean? Translate. No, translate. No. Another word for translate. We did this actually with linear functions last year. Believe it or not.
It will translate up or down on the value of c. Or
up or down. It's a
depending
slide.
on the value of c.
Yeah, it's a slide. It moves up or down depending on the value of c. Well, doesn't it make sense that, what is c again? The y-intercept. So the y-intercept will either move up or the y-intercept will move down based on comparing their c values. So we're going to be comparing a values and c values. We don't even care what the b values are. Thank goodness, because that's the really challenging transformations. We only have to worry about a and c. Did it get wider? Did it get skinnier? Is one opening up? Are they both opening up? What's going on? And then is one moved up or moved down from the other? So it says right here, this is kind of important also. Let's put some arrows by these guys. If the absolute value of a is less than 1, the graph is wider. If the absolute value of a is greater than 1, the graph got narrower. So it's like the bigger the absolute value of a gets, the skinnier. It closes the parabola in. The smaller the absolute value of a gets, it opens it up. It widens out that U-shaped graph. Okay, so these are just like some examples here of like what happens when, so we have compare the graph of g of x. Why is that one called g of x? Well, it means it's a new function of f of x. It just got a new name, so we call it g of x, and its name is 1/3 x squared. So this is what it started as. F of x is the first one. It's always like the starting one, and any letter after that means this is the transformation of it. So f of x became g of x. So what changed? Did the a value change?
Yes.
Yeah. The a value changed, didn't it? What did it change to? Change from what to what?
From 1 to 1/3.
From 1 to 1/3. Let's write that here. This one has an a value of 1. This one has an a value of 1/3. And notice what happened on the graph. Look at the graph and find which one is the parabola of f of x.
This one,
The dashed line one or the solid line one?
dash line.
Dashed line one is the f of x equals x squared. And the solid line one is the g of x equals 1/3 x squared. Did f of x get wider then or skinnier? Did f of x get wider? G of x, I mean. Did g of x get wider? So here you said here the dashed line one is f of x. You're telling me the solid line one is g of x. So we compare g of x to f of x. Here's f of x, here's g of x. What happened?
G of x got wider.
G of x got wider. And notice the vertex stayed the same. In other words, it did not move up or down. Why not?
Because it doesn't have a C.
What are their C values? They do too have a C value. What are they? They have a vertex. They have a C value of 0, which is their vertex, and they both have the same vertex, don't they? So it didn't slide up or down because they have the same vertex. And notice on the graph they have the same vertex. So that's what's when the a value changes. This is the only thing that we worry about is the width or opening up and down. And then on this one now, they say we transform the parent function. This time our new transformation is called h of x. So what's the a value for this one? What's the a value for x squared minus 4? 1. What's the c value? -4. Notice we don't even care about the b value today. We want the a value, we want the c value. So write that down. What's the a value for the parent function? 1. And the c value is 0. So the a value stayed the same, didn't it? So here's the thing. It looks kind of deceiving because here's what happens. When it moves down, which is what happened because the c values are different, when it moves down, then it's got more room to climb, so it actually looks like it got wider, doesn't it? It looks like this one is actually wider than the parent function, but it's not. It didn't get any wider. The only thing that happened is it translated down 4 units. So notice when we talk about translation, we have to talk about what direction. Did the vertex move? Did it move up? Did it move down? Well, it moved from 0 to -4. So it moved from 0 to -4. So it moved down in how many units? 4 units. The vertex of both of them helps us decide that. Okay? So let's go do some of them. We're going to put them in our graphing calculator to help us graph them. Okay, so f of x equals x squared. When you go to turn your calculator around, go to y equals. Clear out anything that's in there right now. And we're going to put in x squared into our y sub 1 with the parent function x squared. So you have to use the x key, which is next to the alpha key, and the squared x squared key to square it. So now it should say x squared in there. Now in y sub 2, we're going to put the g of x function, which is 2x squared. So put 2x squared in the y sub 2 function, or at our place. Okay, we're going to use the table to help us make points for this. So I want you to go to second graph. That's where the tables are. Second graph. I want you to see if you can tell from the table now. Here's what should happen. You should have an x column. You should have a y sub 1 column that has some y values. You should have a y sub 2 column that has some y values, right? Am I correct? Okay, so I want you to go scroll, let's just concentrate on y sub 1 right now, the first equation. I want you to go ignore the last column, and I want you to go find where's the vertex for this one. You should be able to see symmetric behavior going on with the y's. You should find the spot where it makes its turn and the y values start repeating again. What's the vertex for this one? 0, 0. Everybody get there on your table. Find where x is equal to 0 on your table and kind of let that be in the middle of the screen. What's happening on either side of it? So what are the y values on either side of it? Pardon? 0. Okay. We should have a 0, 0. Here's what should be happening in that table. Where we have 0, and I'm going to put it down here, you should have a y value of 0. We're not paying any attention to this column right now. We're not paying any attention to this one. So we have 0, 0. This should be negative 1, negative 2. This should be positive 1, positive 2. Do the negative 1 and the positive 1 have the same y values? In the table? What are they? What is it?
1 and negative 1 are the same ones, which is 1, or negative 1 is 1 for y1, and
I don't want y2. Don't even talk to me about y2 right now.
1, positive 1 is 1.
Okay, they both have 1s, don't they? What's this?
4.
4 and
4.
4. Because when you square negative 2, you get 4. When you square positive 2, you get 4. When you square 1, you get 1. When you square negative 1, you get 1. When you square 0, you get 0. Let's go put those points on our graph right now. Go to your graph and put on your notes handout you have right here. Let's make that graph. And with a dashed line, we're going to draw the parent function. So we're going to dash our parabola for this. Okay, everybody's doing this on their papers. You're doing this, or you're going to do the old-fashioned way of taking or figuring out the points for the graph. We stole them from the graphing calculator. And then at the end of that arrow, I want you to write that at one of them, at the end somewhere, I want you to write that's our f of x function. Okay? Identify that as the f of x parabola. Okay, now we'll go back to our graphing calculators. If it turned off or you turned it off, just turn it on again. If it doesn't take you back to the table, just do second graph and it'll take you back to the table. And now we're going to go check out where is the vertex for this one. So in other words, here's how we could tell the vertex. There's a 0, and then on either side of it, there's the symmetrical behavior. So what's the vertex for the other one?
0.
That one's 0 also, 0, 0?
Yep.
Okay. So now we start looking when it's negative 1, what do we have?
2.
2. When it's positive 1, what do we have?
2.
2. When it's negative 2, what do we have? 8. When it's positive 2, it is 8. Okay, well there's 5 points for that one. Okay, let's go put those on our graph. And this one will be a solid curve. Okay, I got some people who have got their faces scrunched up like they're not even here with us. Okay, this is not good. What's the problem? Okay, this is ordered pair 0. This is ordered pair 1, 2. This is ordered pair 2, 8. Anybody else have the same issue? Create that per table. It's got decimals in the x column. Anybody got decimal x's? Okay. Okay, and then you can, after you've done the graph, go ahead and hit the graph key on the calculator and see if it looks like yours. It doesn't dash one and make one solid. It graphs two parabolas, right? Okay, so that's going to be. Don't be impressed if you want to graph it. Okay. you might have to do a zoom 6, okay, for the graph. If you press graph and it says quit, then clear that and do a zoom 6 and I gotta go check your folds because you got a lot on, that's why. None of those can be darkened when you're in this, so always check that when you get a graphic calculator. So now you should have a press graph. Should be over it?
Yep.
Okay, good. Anybody else not able to get, both parabolas should be showing up on your graph. How come you only have one parabola on your graph? Okay. Everybody got 2 parabolas on their graph? Because you need to go in here and do what I said for the other equation, 2x squared. Okay, so we're going to compare these by talking about what transformations occurred. So let's talk about, let's put this one down first underneath here. F of x equals x squared. And we have the g of x equals 2x squared. Let's identify the a and the c for both of them. For the parent function, it's always going to be a equals 1, c equals 0. So as soon as you see the parent function, just that x squared, you know a is 1, c is 0. How about a for the g of x function? 2. And c? 0. Okay. So now what we do is we're going to just algebraically decide without even looking at the graph for a moment, and then we'll see if our graph supports it. So to be able to compare them to see about their width. Okay, so first of all, they both open up, don't they? Am I on the same notes as you guys? Yeah, oh, that was homework. That's what the difference is. Okay. Okay, so let's first state. Number 1, because they both have a positive a, they both open up. That's what we should expect on the graph. And then, do they both open up? Okay. Number 2. So the a value is going to do 2 things for us. It's going to decide if what direction they open. Do they both open up? Do they both open down? Does f of x open up and g of x open down? Whatever. Okay, so we're going to talk about that first. Then we're going to compare their absolute values. Okay, so we always want to see what happened to g of x. So we're going to say the absolute value of 2, because that's the transform function. How does it compare to the absolute value of 1? Leave a space in between there. Is it the same? Is it larger?
Greater.
It's greater than. The absolute value of 2 is
2.
and the absolute value of 1 is 1. So the absolute value of 2 is greater than 1. That tells us that g of x got what? Remember, go back up here. Up here, up here, up here, up here, right here. Did it get? It's greater than, right? So if the absolute value is less than 1, okay, so maybe what we should do instead is, I don't know. If the new one is wider than the old one, if the absolute value is greater than the absolute value of the other one, that means that g of x is narrower. If that's too confusing for you, the other thing you could do is you could say the absolute value, I'm just going to show you, if you want to do that, you can do this. You could say the absolute value of 2 is greater than 1. In other words, what's its relationship to 1 like it says up above? If the absolute value of a is less than 1, then it's going to get wider. If it's greater than 1, it's going to get more narrow. Okay, so I think this might actually be a little bit better way to compare them. Let's do it this way. Let's change it. The absolute value of 2 is greater than 1. 2 is greater than 1. Which makes it then narrower because it meets the standard of the absolute value of a is greater than 1. Okay, that's the reason. Okay, those are the 2 things that a will do. Those are the two things A will do. We'll talk about their openings, and we'll talk about their widths. And we're comparing g of x to f of x. Okay, the next thing we compare is, did their vertices move? Do they stay the same? Are they in the same place, or is one in a different place than the other?
Same place.
They're in the same place. So number 3, vertex stays the same. So just a little note too. All the ones we're going to do, the vertex is always going to be on the y-axis. So you can always just compare the y-intersection. You can always just compare the c's. It's the b that moves it off of the y-axis, and that's why it's a good thing we don't have to do that. The c's tell us that it's going, and because none of ours, all of the ones we're going to do, b is going to be equal to 0. So that we learned yesterday that means the vertex is on the y-axis. It is the y-intercept. So all we have to do is compare the vertex of each of them. If it stays the same, then we know it's not going to translate, right? So let's just put here, no translation. Put that in parentheses behind that so you know that there was no translation because the vertex stayed the same. When I made them do something else in notes last year that I'm not going to make us do. So we're going to stop with that on this one. Now let's see if the graphs support it. We say they both open up, yes? Okay, we say that g of x, the one that's solid, is skinnier, is it? Okay, we say that the vertex stays in the same place, did it? Okay, then we're good. Okay, let's try this one. Go to your y equals. Clear out only the y sub 2 one. Leave your parent function in y sub 1. No reason to take it out because we're working with the parent function again. And then for the y sub 2, you're going to put in x squared plus 5. X squared plus 5. Okay, so we can keep those same points here, these same points should show up in the y sub 1 column. So everybody got those both in? So we have x squared in the y sub 1, we have x squared plus 5 in the y sub 2. When you go to your table, second graph, find this part of the table. Find this part of the table right now. Okay, so we have all of these. Let's go graph that one again. We'll graph those points right away. Get those on there. And make a dashed line for those. That's our parent. It's the one that's going to move. It's going to change. Okay, now our x squared plus 5, our y sub 2. Fill in tell me what the values are for me to put up here for us. What's this? This is 5? 6? 9, okay, and I'm going to say this is 6 and this is 9, am I right? Because of the symmetric behavior, right? Okay, so go put those points on your graph for the g of x function. Oopsie, I have the wrong spot. That's why I ordered here -2, 9. And +2, 9. Oops, h of x, not g of x, isn't it? Call this one h of x, not g of x. Okay, now, right now, just looking at their graphs, let's just, like, not even comparing anything with their A's or their C's, just looking at the graphs right now, tell me all the comparisons you can make. They both what? They both open up. Okay. Remember the other thing that the A value is going to control, that the first thing we're going to think about is the width. Are they the same width? They don't look like it on the graph, do they? It looks like the one that is up higher, the h of x function, is actually skinnier. Why is that? Because it's been moved up, and so the other one's been climbing. They really are climbing at the same rate. It's just that the width so the width really does stay the same. And we're going to be able to tell that when we compare their A values, okay? When we compare those. So we can't be deceived by the graph. That's what we have to do. We have to look at the A and the C values to help us out. Okay? Did the vertex stay the same? Are they in the same spot? No, that's clear they're not in the same spot, right? And in fact, the vertex of the new function did what? What did it do? Did it move up or did it move down? It moved up. So what do we call that kind of transformation that moves up? Noah, what kind of transformation is this? No, that's not the word for that. It did move up, but what's the transformation word for that? Also starts with the T-R-A. Translation, yeah. Okay, so let's go describe these. We have our f of x equals x squared. We have our h of x equals x squared plus 5. A equals c equals. So for f of x, a equals 1, c equals 0. It's our parent function, right? How about h of x? A equals 1, c equals 5. Okay, our first comparison is going to be with their a's, the direction. What are we going to say? Both open up. They're both positive A values. So both open up. How about the other thing A controls? A controls the what?
The
width of it, okay? So we're going to compare their A values. So we have A is equal to 1. We have A is equal to 1 over here. Remember, we're going to take the absolute value of the second one, and we're going to say, what's its comparison to 1?
The same.
It's the same. It equals. It didn't get smaller. It didn't get larger. So what happens to the width?
It's the same.
Yep, it's the same width. It is the same width. H of x did not get skinnier, even though it looks like it did, because they have the same A values. The absolute value of the A value is not less than 1. It's not greater than 1. It needs to be greater than 1 to get skinnier, and it's not. So it's really, they have the same width. Okay, and last but not least, 3, the vertex. Vertex. Oh, well, we got to know what the vertex is.
Vertex is not the same.
Okay, where do we get the vertex from?
Here.
Remember, we're doing ones where there are no, the B value is what?
0.
0. So when the B value is 0, the vertex is the same as the y-intercept. What's the y-intercept?
0 and 5.
So what did the vertex do?
Changed.
H of x. Did it move up? Did it move down? Did it? Okay, vertex moved up. And our graph supported that, didn't it? It moved up. Okay, so that means that what happened? What transformation then? Translation. So we can say it translated. And when we talk about a translation, we talk about how far and what direction. 5 units.
5 units up.
And up. Or you could say up 5 units. That doesn't matter. We're going to talk about both though. What direction would I expect on a graph? How far? Okay. Well, we got to learn how to do this without a graph. So hopefully that's the first thing we're doing in the backside here. I'm going to leave that one for you guys to just study on your own. We're going to go to number 3, where they actually do have a graph for us, just as a visual. But we're going to compare them, and we're going to use the graph then to help support it, okay? So let's do this first. A equals, C equals, A equals, C equals. Compare the graphs of g of x equals negative 2x squared minus 1 and f of x equals x squared. Which one was the starting function really? Which letter comes first in the alphabet? F. So f of x is the starting function, g of x was the result. Even though they wrote it first, it was the result after the transformations, okay? So what's our a value for g of x? Negative 2. What's our c value? Negative 1. Notice what's our b value, even though we're not going to use it? 0. So remember, we're doing just the ones where b is always equal to 0. And for our parent function, we know 1 and 0, right? Okay. So what's the first thing we're going to compare?
One do it, let's go down.
Okay, we're going to say that. So which one's opening up and which one's opening down?
F(x) is opening up.
Okay, why is f of x opening up? What would be our reasoning if we didn't have this graph here to look
Its
at?
A is positive.
Okay, f of x opens up. And g of x, because it has an a value that's negative, what should it do?
Opens down.
And g of x opens down. Some of you aren't going to get, I can already tell you're not going to get a stamp tomorrow because you're not going to have good enough notes to guide you. F of x opens up and g of x opens down. That's our first comparison, their openings. Okay, next comparison is their what? What happened to the a value for width, right? So we're going to go with our the absolute value of our g of x function, the absolute value of our g of x function, absolute value of its a value, and then compare it to 1. Is the absolute value of negative 2 1? Is it equal?
No.
What is the absolute value of negative 2?
2 less than.
2, so is 2 greater than 1? Yeah. Okay, when the a value, the absolute value, is greater than 1, what do we expect?
It's open up. Or open, or be wider.
This way or this way? Narrower, remember? See, it's kind of like the opposite of what you think would happen. It's kind of like if you multiply something by a number bigger than 1, we think it should get, like bigger. But what it does is it closes it in this case. So we're going to say that g of x is more narrow or narrower. I don't know. This is always the fun one. How did I put it in my notes here? Narrower. Yeah, that is what. I think I go back and forth. I use. Yeah, I did. That's what I thought. You can use all kinds of ways to say it. More narrow, or narrower, or skinnier. I'm just going to start using the word skinnier. So much easier. Okay, so now we've compared their widths. We've said the new function is not as wide as the old one. Okay, so now we're going to move on to talking about their c values. So we're going to look at their c values. So here's our parent c. That's where the vertex is, remember. This is our vertex. Here's our transformed functions. C, there's its vertex because b is equal to 0 in both of these. So what happened, Noah?
We have found the vertex of F.
What does that tell us, though? No. Okay, just stay away from this, okay? What happened to the vertex? Did it stay the same? Is it in the same spot?
No,
Did it go up? Did it move down?
translated down.
Okay, so the vertex moved down because it went from 0 to negative 1, so that means it translated, and there's our clue right there, down, and what's the change between the c's?
1 unit.
1 unit. It went from 0 to negative 1. And we're going to stop with those 3 descriptions. Okay, now we're going to do 4 and 5 without graphing.
And that's what you're gonna probably be doing sometimes in your homework, because we have to be able to use the A and the B values to do, or the A and the C values to do it. So, what do you suppose we're gonna do first? A and C. A equals C equals. A equals C equals. Write down the function, identify their A's and their C's. Two things, the first two things you compare have to do with their A value. So what's one of the things we're going to say? Yeah, so what are we going to say? Both open up. They both have positive A values. So both open up. We don't even have to put them on the graph to tell that. Other thing we do with their A value. The absolute value of this A, the transformed one, right? Absolute value of 1/4. How does that compare to 1? Is less than. The smaller it gets, the wider it gets. So we're going to say that g of x is wider. Last but not least, we compare our vertex. So again, this is where we do that. We go to the C values because B is equal to 0 in both of them. So the vertex is the y-intercept. What happened with the vertex? It went from, so here's where it started, remember? And now it's here. What did it do? Moved up. Okay, that tells us then it translated 4 units, went from 0 to 4. And what direction?
Up.
Up. Okay, one to go. Stay with me. A equals, C equals, A equals, C equals. Okay, what's going on in this one? First thing we're going to talk about. One of them's got a negative A value, the other one's got a positive. So what do? One opens up and the other one opens down. So let me let you off the hook and make this a little easier. Both. Oh, no, we don't even have to say that we're both. I don't even know why I'm doing that. Open opposite directions. We should expect on the graph one's opening up and one's opening down. Okay? Open opposite directions. Okay, how about the other thing we do with A? Absolute value of -5 compared to 1 is greater than, because the absolute value of -5 is 5. 5 is greater than 1. Maybe some of us should be just putting that, huh? Maybe that would look better. If we end up with the absolute value of A being greater than 1,
H of x is skinnier.
yeah, then H of x is skinnier. Okay. We'll start using that word. Do you know how to spell skinnier?
It's S-K-I-N-N-E-R.
I-E-R?
E-R.
Yeah, skinny is with a Y, but that Y changes to an I, right? Am I right? My English people in here. Okay, number 3. Now we compare their C values. Did the vertex stay the same? No. So it moved. So the vertex did what? Moves down. Okay. because apparently it went from a 0 to a -1, okay, so that means it translated down, how far? 1 unit. You don't say -1 unit, the down took care of that, okay? How far and what direction? Whew. Okay, let's get those graphing calculators returned.